So the difference between the conventional steam power plant and the organic Rankine cycle is in conventional steam power plant with the working fluid is steam. So the steam, in order to get power from the steam should be at a very high temperature, normally above than the 500 degrees C, and the pressure is again very high pressure, like the 200 more 250 bar, sometimes 300 bar. So that's a very high pressure. To produce high pressure and high temperature steam, obviously the energy requirement, the fuel combustion is very high, and that means that's very expensive one. Now, in case of the organic Rankine cycle, the working fluid is a refrigerant. So the a refrigerant, you know that it takes a little heat, it vaporize. It vaporize mean you are getting vapor. So if we provide sufficient amount of heat to the refrigerant, then we can get a superheated vapor. So superheated vapor here they can run the turbine, right? So that means the component are the same except a turbine. I mean a compressor in the we are using compressor in the refrigeration system, whereas in organic Rankine cycle we are using a turbine for expansion. In compressor we produce compression, in turbine we produce expansion. So basically what is happening in an evaporator, in a evaporator the liquid refrigerant enters here, and then that liquid refrigerant get heats from the heat source. I mean that heat source could be the solar energy, it could be the condensate. So that condensate or the heat from the solar energy is is provided to the refrigerant. Then that refrigerant vaporize, it becomes vapor. Let's say superheated vapor. Then superheated vapor they drive the turbine, and then we get some work output. Then at the here we use a condenser. So here condenser is this one. What is happening in condenser? The vapor, they are again converted into liquid refrigerant. So that means we need a cooling water in and cooling water out. So that means here again the liquid refrigerant is produced. So that liquid refrigerant with the help of a pump is again sent back to the evaporator. So in this way, we can continuously produce the power in the turbine. So in heat source, it can be condensate, let's say hot water, let's say hot water that is obtained from the solar energy, right? So that hot water when come in contact, through a heat exchanger, evaporator is a heat exchanger. So that means, so we got the superheated vapor. So the question here is now how to model this process. After modeling the process, how to simulate that process, and then how to check the impact of pressure, pump pressure on work output. Similarly, what is the impact of various refrigerant. Similarly, what is the impact of turbine expansion, outlet pressure, right? And similarly, what is the impact of the area versus source temperature. So we can also use different refrigerant, and what is the effect of different refrigerant, right? So we can all analyze this using the modeling and simulation tool. So let's practice this with the help of the Aspen Plus. Let me open that. So it's a new simulation. It's giving some license error. Let me try with some. class. Right, so this is a blank simulation. So what should be the first process? Obviously, first process is, as I mentioned in the previous class, that there are four modules. First of all, you need to mention what are the component and what is the property method. And then you can develop your simulation method. So first of all, I mean, you need to define component. What are the working fluid that will be used in your simulation? So let's say, what are the working fluid? Any one of you, can you tell me what are the working fluid that will be used in the simulation? Anyone? So 211, he has performed the some simulation. Can you tell me 211? What are the working fluid that will be used in this simulation?
Sir, firstly, we need the propane or an organic refrigerant,
Yes, right.
and secondly, water.
Yeah, so that means we need to define two working fluid because we have the water here, similarly the water here, and the other working fluid is the refrigerant, right? So first of all, we need to define one is refrigerant. Let's define any of the refrigerant. Normally in organic Rankine cycle, a list of the refrigerant are used. For example, the refrigerant that are used, they are mentioned in this table. So R134A, R245FA, right? This one, and this one. Let me randomly choose, let's say R254FA. Let me choose this one, right? So let types here are 245 FA, right? So this is the refrigerant, first working fluid, and the second one is water. So these are our two working fluid that will be used. And then we need to define the property method, right? This one, the property method. So from property method, we can choose Peng-Robinson equation of state. So there will be Peng-Robinson equation of the state from the property method. So PEN, yeah, that's Peng Robinson equation of state. Right. So now our property is already chosen. We can also define the units, that which units by default it is already selected this one. So what is the meaning of met C bar? So this is the met C bar. As you see, the flow rate will be mentioned in kg per hour, mass, mole flow, volume flow, right? Similarly, the heat, you can see what are the properties of the heat, right? So these are the units that will be used in this simulation. Now the second part is developing the model, right? So this is the flow sheet on which you can develop your model. Now again, if you look at that, what are the components that will be used? You can see. So first of all, we need an evaporator, then a pump, then a condenser, and then a turbine. So mainly we need four different components, right? So here we can first of all, let's say evaporator. So evaporator is a kind of heat exchanger. Now this heat exchanger will be different than the previous heat exchanger that we have used. I mean, previously we used this heater, but now in this simulation, we need to require that the refrigerant pass through, and then we have to heat exchange through a hot water, because that heat will be given to the evaporator so that we can get here the superheated vapor. So that's why we will use different type of the heat exchanger. So the this type of heat exchanger will be used. Right, so let's name it as evaporator. Evaporator. So this is our evaporator, and then after evaporator we need a pump as well, right? A condenser as well, right? So let's say this is our condenser, COND condenser. Let's given the name condenser. Then we need a pump as well, a pump as well as a turbine. So pressure changer, here is a pressure changer. We need a pump as well. So here is a pump, PUMP pump, and then we need the turbine. So this is compressor and the second one is a turbine. So let's say this is TURB. TURB mean turbine. Right now we can rearrange the component. I mean, let's say uh, the pump will send the refrigerant to evaporator. Then from evaporator will produce superheated vapor and it will go to the turbine. So after turbine, then it will go to the condenser and then condenser again to the pump. Now we can connect the component. For example, from pump, it will be like you have to read that this is cold in. Can you see on the screen? This is cold in. So from the pump, the cold in will enter into the condenser. Right. So let's say let's give the name. Let's say one. Right. Then from cold in, so this is cold out. So cold out, then it will be connected to the inlet of the turbine. Right. Then let's say give the name. Let's say two, and then from the outlet of the turbine it will be connected to the condenser. So condenser mean hot, hot in, right? That's hot in. Let's say this is 3 and then we have hot out, so that will be connected with the help of pump, right? So let's say give the name, let's say 4, right? And then for example in evaporator we need to have some hot water. Let's say this is hot in, hot water in, right? And then some hot water out, hot water out, let's say. Right? And similarly in condenser, to condense the vapors here, we need some cold water again. So cold water in, let's say cold water in, and then cold water out, right? So now you can see our sheet is almost completed. We can flip it. Here is option for the flip. So let's say we have flipped that. Similarly, we can flip this one, right? Uh, Further flip. Yeah, that's much better. Okay, anything else? We can also move this up and down. Okay, right. So I think our flow sheet is completed now, right? So that means this is our model. Like the from the evaporator, I mean the liquid refrigerant from the pump, it will enter into the evaporator. And in evaporator, what we are giving the hot water, let's say. And this hot water can be produced from the solar energy, it can be produced from the condensate. So there could be any source of the heat. Let's assume that we have some hot water and that hot water when enter into the evaporator through the heat exchanger, then the liquid refrigerant will be converted into vapors. So those vapors when enter into the turbine, then it will produce power, right? So that power, I mean that power, that again that vapors after expansion it will enter into the condenser. So in condenser we need to cool down that refrigerant, so we need some cooling water. So cold water in and cold water out from the condenser. So as a result, at the outlet of the heat exchanger we'll get a liquid refrigerant. So that liquid refrigerant again pump will throw to the evaporator. So this process will keep on continue. So we'll get some output power in the turbine. But now obviously we need to give some, I mean parameter for each of the component and some flow rate. So let's start from the pump. Let's start from the pump. So that means pump will produce some pressure. So let's say the discharge pressure is, let's assume 5 bar, right? So 5 bar is the pressure for the pump, right? And then in heat exchanger, what we want in the heat exchanger, we want in the heat exchanger that, let's say instead of one, we give the name, rename that stream refrigerant, and the name of that refrigerant is, let's say R254FA, the refrigerant that we use. So this is a refrigerant line, right? So that refrigerant when enter into the compressor, then what we want at the outlet, at outlet of the heat exchanger, we want here superheated vapor or at least dry vapors, purely dry vapor. We don't want here any component of the liquid, because if the any component of the liquid enter into the turbine, then turbine can be damaged. So we don't want outlet of the heat exchanger any of the vapor. So here we need to define some parameter. For example, it is asking for some specification, heat exchanger specification. So there are many options here for this specification. You can read that hot stream outlet temperature, hot stream outlet temperature decrease, hot outlet cold inlet temperature difference you want to mention, hot stream outlet degree. uh, yeah, we want basically the cold stream, basically the cold stream which is entering the outlet of the cold stream, we want the superheat, right? I mean the purely vapors. We want this, this cold stream of the refrigerant which is entering into this heat exchanger. The outlet of the cold stream, we want the superheat, right? We want the cold stream outlet degree as a superheat. So let's say that this is purely dry vapors. So 0 degree mean this is uh, purely dry vapors. I hope you know that. Just to recall you, you know that in the Rankine cycle, just to recall you the Rankine cycle, that the first component, let's say from pump, the pump increases the pressure isentropically, then it enters into the boiler. Here the boiler is our evaporator. So in evaporator, what is happening? The refrigerant is converted into superheated vapor. Now, since this is the degree of the superheat, the degree of the superheat. In this case, we have not given any degree of the superheat. That means zero. Zero mean here completely dry vapor. So completely dry vapor will enter into the turbine. Then after expansion, right, it will give you the expansion. Then in condenser, again the heat is removed. So this, I hope you are familiar with the Rankine cycle. So the same is happening here. We need to mention some. Let's say I'm giving you the pure 0 degree, I mean the pure dry vapors, right? And after that, it enter into the turbine. So in turbine, again we need to mention that this is a turbine, and this is an isentropic turbine. Type of the turbine is, let's say, isentropic, and let's say I assume purely the isentropic efficiency of that turbine, right? And we also need to mention some discharge pressure, that how much expansion you want to go. Let's say the outlet pressure, let's say 2 bar. Okay, let's give any of, let's say 2 bar. And then after the turbine, it will go into the condenser. So what we want in the condenser, we want in the condenser the outlet of the condenser. Just I showed you here what we want in the condenser. For example, what we want at the outlet of the condenser, that it should be purely subcooled region. This is a saturated liquid, I mean pure subcooled region. So again we can mention the properties of the condenser, that in what are the specification of the condenser, that there are many option for that. So the hot outlet, what we want, hot outlet subcooled. So here is hot stream outlet degree subcooled. So let's say it's purely subcooled. So let's say 0 degree. Okay. And then the next one is pump. So I think pump we have already defined. Okay, pump we have already defined. And then we need to define some the properties of the refrigerant. For example, this was the refrigerant. What we want here, I mean here, what we want here, let's say the pump is sending the refrigerant as a liquid, right? So liquid mean there is a zero fraction of the vapors, and let's say pressure is, let's say 2 bar, and the flow rate is, let's say mass flow rate is given to be let's say any of this, let's say 3600 kg per hour, and this is purely refrigerant. There is no water in that line, purely refrigerant. Okay. And similarly we have the water entering into the and the cold water is entering. So let's say we need to define the hot water. So hot water that is entering in, I mean, as a source of heat, let's say the hot water available from the condensate or from the solar energy is, let's say, 100 degrees C. That temperature is available, and let's say that's at 1 atmospheric pressure, right? So let's say that's in 1 atmospheric pressure and 100 degrees C, and it has certain mass flow rate. So let's say you can give any of the mass flow rate, let's say 40,000, and this is purely water, right? This is purely water. And similarly, we need to define the cold water as well. That let's say the cold water available is, let's say, 20 degrees C, okay, let's say 1 atmospheric pressure, and it has certain mass flow rate, let's say 30,000 kg per hour is the mass flow rate, and it's purely water. Okay. So after you define all of the information required, you will get a message here that the required input is complete now. Right? Once the required information is complete, now you can run for the simulation. You go to the home. So in home, you can see that you can run the simulation, and it will run now. After running, you can see from the control panel, is there any error? So you can see there is no error. So here is the option for the error. It gives you some error initially, because initially when it simulate, I mean, it start from here, but there is no, I mean, in the, because there is a iteration process. Those who are those who have studied the numerical analysis, they know that when you give some initial condition or the boundary condition, it start from here. But at the same time, there is no refrigerant here. So in the first loop, some of the component will have without the refrigerant, but the second loop, then the refrigerant will be available. So that's the error message, that in the first loop there was no refrigerant. We know that. Okay, so the results are available. I mean, if you look at the results, let's say, let me show you, there is a button for modify. So if you click on the temperature, pressure, and vapor fraction, I mean, you can see that, okay, that what is happening everywhere in the model. For example, I mean, let me show you. Okay. So that circle will represent the temperature, this will represent the pressure, and the last one is the vapor fraction. For example, here that refrigerant enters at 5 bar pressure and 34 degrees C. So when it enters into the evaporator, there is a hot water, the water is entering. So this hot water will convert that, zero means zero vapor fraction. So this is completely liquid. So after that, it is converted into completely vapors. So you can see from 0 to 1, because this represents the vapor fraction. So 0 to 1. Now that refrigerant is completely vapors, and the pressure is again 5 bar, but the temperature is a 63 degrees C. So from 34 degrees C to 63 degrees C. So can you imagine that refrigerant, I mean, that refrigerant R245Fa is in the dry, uh, I mean, saturated vapors now. So saturated vapor can be used to drive the turbine. Whereas if you use the steam here instead of the refrigerant, if you use a steam here, steam cannot be at a superheated state at this temperature and this pressure. We need a huge energy, I mean, to convert that steam into superheated, or to convert that into dry saturated vapors, right? So anyway, so once that dry vapors at 63 degrees C and 5 bar pressure enter into the turbine, then there is expansion. I mean, from 5 bar 63 degrees C, the expansion takes place in the turbine isentropically, because we have selected isentropic expansion. Then at the outlet of the turbine, these are the conditions. I mean, the temperature will decrease from 63 to 40 degrees C, and the pressure will decrease from 5 degrees C to 5 bar to 2 bar. And still we have the completely vapors. So these vapors, we need to again convert these vapors into liquid. So what we'll do here, we'll use a cooling water here. So cooling water is available at 20 degrees C and 1 bar. So once that through the heat exchanger, When that cooling water comes in, then its temperature increases from 20 degrees C to 25 degrees C, right? And then as a result, that vapors from 40 degrees C it comes to the 33 degrees C, and now zero mean that's completely liquid, zero vapor fraction. So that completely liquid state of the refrigerant will enter into the pump. That pump will again increase the pressure up to 5 bar, then that will send through the evaporator. So this process keep on continuing. Now we want to know that how much is the work produced by this turbine, right? How much is the work produced by that turbine? So there is an option to know the work produced, because this is a material stream. I mean, all the stream that we have mentioned here, they are the material stream, but we need to know the work or heat. So this is the stream for the work. So let's say if you click on that work, so then you will see, I mean, outlet says this is the output. When you click at the back, that will indicate the input. So because from turbine we get the output, so you click here. So if you click here, so let's name it as work. W mean the work output, right? So this is the work output. So again, you go to the home, reset, okay, reset, and again simulate. So if you again simulate, you will, I mean, you can see that work. So we need to represent from modify. You click on the modify and there is a tab, it called heat slash work. So if you click on that heat slash work, now again you can see the work here. Can you see that? So that means how much work is produced? 17 kilowatt. I mean, if you right click on that and you click on the results, so you can see that the work produced by that turbine is about 17 kilowatt. Right? So that turbine work is about 17 kilowatt. Whereas how much heat is rejected by the condenser? It's very huge. I mean, in terms of kilowatt, that's 45,894 kilowatts. Similarly, how much heat is absorbed by the evaporator? That's 49,739 kilowatt, right? Similarly, how much input is required for the pump? About 1 kilowatt input is required. So if you know that heat absorb, heat rejection, similarly the work output, work input, you can also calculate the efficiency of the organic Rankine cycle. Organic Rankine cycle mean what is the output divided by the input, and input is in the form of the heat input, or you can also calculate q in minus q out divided by q in. So there are different way to calculate the efficiency of the Rankine cycle or the organic Rankine cycle. Now this is the simulation and modeling process. Next one is, I mean, we want to see its performance. In other word, what is the performance evaluation of the organic Rankine cycle? Now, I informed you in the previous class that there are different tools available in that. Even, I mean, you can design. I mean, whatever you want to achieve, you can design. There is an option of the design specs. If you recall that, there is an option of the design specs, right? Any of the, I mean, you can design those flow sheet, and then I mean, there is in the flow sheet, you can design. There is an option for the design, right? So if you click on the flow sheeting option, there is a design specs. So I mean, whatever you want to do for the design specs, for example, let's say you want to get a specified temperature at the condenser outlet, right? You want to get a specified temperature at the outlet, and you can vary the flow rate of the cold water. So you can get that, right? And similarly, let's say if you want to know the performance of the organic Rankine cycle, let's say I want to know that how the output is changing. I mean, the output that we are getting here, how it is changing if I change the pump pressure. Currently, the pump pressure is 5 bar. So let's say if I change the pressure from 5 bar to, let's say, 10 bar or 15 bar or 20 bar, so what is happening with the output? So then which tool I will use? I will use the model analysis tool, let's say sensitivity analysis. So let me do that. So let's say I want to know that there is a variable, vary mean variable. What I want to vary? I want to vary the pump pressure. So that variable is, let's say, give any name, let's say 1, and this is a block variable because pump is under the block variable. So that's a block variable. Which block? Pump, right? And which variable you want to change? The pressure, pre, where is pressure? That's a pressure. So we want to vary the pressure. So let's say I want to vary from 5 to 12. Let's say 5 to 12. And how much is the increment? So let's say increment is 1. I mean, between 5 and 12, the increment is 1. Right? So this is the variable. And what I want to get? I want to get, let's say, uh, work, right? Work of the turbine. It's just a name. You can give any name, right? So I want to know, I want to get the work, right? So what is the type of that you want to know? That's the work or power, right? And from which stream? W, because we have given that stream as a W. If you recall that, we have given this name as W, right? So from W, and then you can fill that tables. That's it. Again, you reset and again simulate, run. Okay. Okay, your simulation is completed now and the results are available. So what the results are indicating? The results are indicating that when the pressure of the pump was 5 bar, the work output was about minus, I mean minus mean, that's just a representation. I mean it in absolute form, that's the work output. So let's say this is the 17 kilowatt is the work output of the turbine. Similarly, for the 16, if when the pressure is 16, you are getting 20. So as the pressure is increasing, the output of the turbine is increasing, right? So let me plot that. We can also plot that. Here is a results curve. So on x-axis, we have the pump pressure, and on y-axis, we want the work. Okay, so here is that. So on horizontal axis, there is a pump, and on vertical axis, we have the work output. So this is how the representation of I mean, you have to read from here to here. I mean, the negative value is actually the opposite one. Okay, so this way, I mean, you can perform any of the simulation, right? This is just one example. Okay. I mean, yesterday somebody asked me that can we have some the template file so that we can use that template file and we start working from the instead of blank sheet, we can modify and we can, yes, we have the template sheet as well in the software. Let me show you one of them. Uh, for example, this is a template for code generation. Okay. So you have studied the Brayton cycle. Brayton cycle is for the gas turbine. I mean, what happens in the Brayton cycle? Let me show you. I mean, cogeneration power plant. So this is a cogeneration power plant. I mean, this is from Thermo 2. I just copy from Thermo 2 that you have already studied. So what happening in the cogeneration? That basically there is a gas turbine. I mean, the air enter into the compressor, right? And then the air is compressed to a high temperature, high pressure in the compressor. Then it enters into the combustion chamber. So in combustion chamber, we enter the fuel. So as a result of the combustion process, hot gases are produced. So those hot gases drive the turbine and we get some work output from the turbine. Then those hot gases are again they are reutilized in the heat recovery steam generator. We call the HRSG, heat recovery steam generator. So this is like a heat exchanger. So but what happened? We use the water here. So that water when entered into the HRSG, it is converted into steam. So that steam is used to drive the steam turbine. Then steam turbine enter into the condenser, then again pump, and so this process keep on continue. So we are getting two work output. One of the work output is from the gas turbine, and the second output is from the steam turbine. So how to model this process? I mean, although this looks to be very simplified, but actually when you model and simulate this process of cogeneration, it will be much complicated. So let me show that in the Aspen Plus. Now, this one is for the, I mean, this is for the gas turbine only, right? In gas turbine, what happens? What we need? We need an air, right? We need an air and some fuel, right? So, I mean, that air and fuel, right? So the first part is the air. In air, we need to compress that. I mean, just to see, show you. I mean, what happened? Air entered into the compressor, so we need to compress that air, right? So let's say that air entered into the compressor. So we need to compress that air in the compressor. So we need to put some values in the compressor, that isentropic compressor, how much pressure we want in the compressor. It's almost, let's say 13.327 bar pressure we want at the discharge. Let's say we have assumed 0.9% isentropic efficiency and 0.98 mechanical efficiency. Then after compression, I mean, after compression, it goes to the some mixing chamber, right? In mixing chamber, we need some fuel as well. So let's say the fuel is also entering into the mixing chamber. So fuel and the compressed air from here that enter, they are mixed, and then it's fed into the combustion chamber. So this is a combustion chamber. So what happens in the combustion chamber? The combustion take place. So as a result of the combustion, the hot gases are produced. So those hot gases, they drive this gas turbine. So this dotted line basically represent the work. As I showed you that there are three streams, right? The solid one is for the material stream, the material flows like the air flows, right? The dotted one that represents the work input and work output, right? Because for the for the compressor, we are giving it as the work input, right? So this is work input, right? Similarly, from the steam turbine, I mean, we are getting some work output. So what is the net? So here, I mean, we combine the work output and the work input. So what is the net work output, right? So it will minus, because one will be negative, one will be positive. So it will subtract. So as a result, we'll get some net work output, right? So after that expansion of these hot gases, where we'll send these hot gases? After expansion in the gas turbine, where we'll send these hot gases? Yeah, anyone? Where we are going to send these hot gases after expansion in the gas turbine? Anyone? 133.
या सर ऐसे हम कूलिंग टावर में सर भेज सकते हैं.
No. I mean, after expansion in the gas turbine, can you see here? After expansion in the gas turbine, the temperature and pressure is still very high. Can you see the temperature and pressure here? I mean, you just click on that and let me show you the temperature and pressure. So how much is the, I mean, what is the temperature here?
Sir, I can't see the pressure and temperature.
So it is, I mean, can't you see at the outlet of the gas turbine? It's 815. Can you see now?
No, sir. No, sir.
So it's available. I mean, it's visible. It's very clear. Still not?
No, sir.
So the outlet temperature is 815 degrees C. So this temperature and pressure will be used in the HRSG. So that means we need to design and model the HRSG now, right? So again, we need a new model for HRSG. So let me show you another one. So this is model for HRSG. So can you see the model of the HRSG? So this is much complicated, right? So basically what is happening, this is the hot gas coming from the gas turbine. It enters into the heat exchanger, whereas the water in the heat exchanger enters and it is converted into steam. So that steam is used to drive the steam turbine, right? That's called the high pressure HP steam turbine. Then further, that is used to drive another turbine, that's called the intermediate steam turbine. Then further it is used to drive another steam turbine, that's called the low pressure turbine. So HP, IP and LP. LP mean low pressure, IP mean intermediate pressure. So this is how the HRSG is designed. I'm not going into detail of this. I'm just showing you the capability of this software, that this software has completely designed a complete cogeneration plant that include the gas turbine as well as the steam power plant, right? So let's come back to your CEP now, right? That's the main objective, that what is your CEP for this semester. CEP, let me show you the CEP. Can you see the screen?
Yes,
Screen
sir.
is visible. Okay, so your CEP is basically, the objective is to produce a chilled water, right? And that chilled water can be produced from the vapor absorption refrigeration system. You know that in vapor absorption refrigeration system, we have evaporator, condenser, and a generator, right? Expansion and an absorber. So there are five component absorber and the expansion valve as well. So we want to produce the chilled water from the vapor absorption refrigeration system. But we know that in the vapor absorption refrigeration system, there is a pump also. That pump is used to feed the concentrated solution into the generator. So we need some electricity, right? That electricity will be received from the organic Rankine cycle, because in organic Rankine cycle we use a turbine, right? So the output of the turbine produce electricity, so that electricity will be fed to the pump, right? And again, what is the heat source? The heat source is a solar energy. So the solar energy will produce some steam, so that steam will be used in the organic Rankine cycle as well as in generator, because in generator we also need to separate the refrigerant and the absorbent, right? So the heat source is a solar energy, so solar energy heat will be used to drive the organic Rankine cycle that I showed you in today's class. So the electricity produced that will be used to drive the pump, and as well as the heat from the solar energy will be used to drive the steam generator. So finally, I want to produce the chilled water. And what is the capacity of the chilled water required? That's 3 tons of refrigeration. You multiply 3 with 3.35, that's very close to 10 kilowatt. So that's the cooling capacity required. So what you need to know, you need to design this system. Organic Rankine cycle integrated system. So integrated system mean the solar heat integration system with organic Rankine cycle as well as vapor absorption refrigeration system. On Aspen Plus, you can have the integrated system. For example, let's say there is an option for let's say, can you see here the user or this one? You can click use in the user model. Let's say you click on that and you can, let's say one model is ORC, right? So inside that, you click on that. So here you can, develop an ORC. For example, ORC mean there will be the heat exchanger, right? Let's say evaporator, right? The condenser, right? And the, let's say, pressure changer, right? Let's say pump. So let's say three component, right? So you, right, and you simulate in that, right? So the output from the pump W that will be used, I mean, from here, the electricity produced on the ORC, right, that will be used, let's say from here, the electricity, not the material stream, sorry, that will be the work output. The work output produced in the ORC, that, I mean, W, that will be used in the vapor absorption refrigeration system. So you will create a new user model here. So let's say another one. So this will be vapor absorption refrigeration system, VARS, right? So in, sorry, in that refrigeration system, I mean, in vapor absorption refrigeration system, there will be absorber, condenser, evaporator, right? And then the third one, you need a solar heating system. So again, you need a third model. That's, let's say, solar, right? So in solar, what happens in solar? In solar, basically, you need steam. I mean, by using the heat input, you need certain steam. So that's like just a heat exchanger. That the heat exchanger, let's say, solar collector. Let's say SOLCO, solar collector, right? So this is our solar collector. So from solar collector, what we want the water in, and let's say one, and at outlet we want some steam, right? Let's say two, right? So let's say the water entering is, let's say we give certain mass flow rate and temperature. Let's say it's one bar pressure, and the temperature initially was, let's say, 25 degrees C, right? 25 degrees C, and it has certain mass flow rate. Let's say mass flow rate is, let's say, 5 kg per second. I'm just giving, I mean, any, let's say this is only water, right? So this is just the water, and what we want this water, we want this water a steam. So you can say we want this water as a steam. So vapor fraction should be equal to 1. We want to convert that water into steam, just vapors at a which pressure? Let's say 3 bar, right? So you can simulate this. So this steam, right? This steam will be used further, I mean, in the next one, like N2, I mean, from here, I mean, that will go, I mean, it will connect with the 2. This is 2, right? And we need in the vapor absorption refrigeration system as well. Let's say that's 3. It also required in the ORC as well. That steam produced, that also will be used in the vapor absorption cycle as well as in ORC, right? So again, in the vapor absorption cycle, you need to develop the complete vapor absorption refrigeration system, right? And that steam, we can go, I mean, we can take at, I mean, use in here, let's say reconnect the destination. So it will go now into the vapor. So this is the input that's coming from this solar power plant, right? The steam. So that steam now will be used in the vapor absorption refrigeration system. The steam will be used in the generator. Generator is like a heat exchanger. I mean, like a heat exchanger. Let's say GEN, right? So that is, this steam will be connected with, I mean, reconnect the destination hot. You have, this is cold, so hot. So this will be connected. So this is steam entering into the generator. So that will go out, right? You have to give certain name for each stream. So here the refrigerant will enter, not the refrigerant, the mixture of the refrigerant and the absorbent, that will be separated, right? So you have to think about that. I mean, how you model that. I can give you certain, I mean, the reference paper, how to model that. You can read those model paper. For example, this is one of the paper. It has modeled the Watom lithium bromide absorption chiller using the Aspen Plus. This is one of the very highly impact factor journal, applied energy. This is one of the, I mean, very very high impact factor journal for the research. So they, in that case, they use the Aspen Plus to model the absorption chiller. For example, you can see they have modeled the complete absorption model. So this is the model. I mean, the evaporator, then absorber, then generator, then condenser. So how they model that? They use the Aspen Plus and model like this way. That this is an evaporator. So from evaporator, it enter into the absorber. Then from absorber, a pump is used. Then from pump, it send into the um, generator, then from generator it send into the condenser, then from condenser expansion valve, then again evaporator. So there is a heat exchanger, right? This is just to increase the efficiency because this is a concentrated solution. So we want that lean solution preheating. This is a preheating before entering into the generator. Similarly, this is pre-cooling before entering into the absorber, because in absorber we want low temperature. So this is pre-cooling, this is preheating. So this is heat received by that. So this temperature will be decreased. Similarly, the cold temperature will be increased. So this is just like the same, this process is same as this one, right? So how they model, I mean, they have also mentioned the properties that at state one, what they use the vapor quality, right? What they have used. I mean, they have also mentioned the different properties as well. I mean, if you read that, they can also give you certain properties as well. They have mentioned and each where what they have used, what were the properties, right? I mean, all the desired input they have mentioned here, right? Even what is the in the stream, what is the mass flow rate for the water, what is the mass flow rate for the lithium bromide. Okay, similarly for this is for the single effect. So the next one is for the double effect. You will just use a single effect, not the double effect. I mean, you have to use the simple one, right? So next, they that's are the results. There is another one. Let's say this one. This is a complete thesis, right? For the how to model and simulate the vapor absorption refrigeration system. It can also help you how to model that. I mean, it has explained very detailed method how to model the vapor absorption refrigeration system based on the lithium bromide. Okay. There is another one. This paper also it has explained how to model the vapor absorption refrigeration system. It has modeled in a different way, right? I mean, it has modeled in a different way. I mean, it has mentioned all the temperature. I mean, the properties, what should be the temperature of the condenser, evaporator, right? Absorber one, absorber two, because it has used a multi effect. It has used the double effect, but you will use just the single effect, but you can get the properties. I mean, that's very common from the literature. You can get what should be the temperature and pressure. So accordingly, you can model and simulate this integrated model. So I hope you understand that. Now let's come back to the questions. And any question? So is it clear to everyone?
सर ग्रुप प्रोजेक्ट होगा ना सीपी ग्रुप प्रोजेक्ट होगा
Actually, you are just 12 people. So making group mean there will be 3 or 4 groups only. So okay, let's try for the group. You can have maximum 3 people in a group. Okay, so there will be 4 groups only.
ओके सर
Okay, actually, this is a very good opportunity for you to design and model and simulate an integrated solar ORC and vapor absorption system. So if you're capable of, I mean, modeling this system, even I think it is publishable. I mean, you can publish in a conference, you can publish in any of the technical workshop. That's very interesting project. I mean, if you put some effort, I hope you can do that. That's not very difficult. I mean, if you have any problem, any difficulty, you can come to me. I mean, I can guide you. But again, it's up to you. Okay, how much effort you put in that assignment, right? Any other question?
Sir, deadline
On the CEP की deadline, तो you know that. I mean, regarding the CEP, that's very clear. I'll email you. So in that you can see all of the information. For example, there are two phases for that. The phase one is 4 weeks after mid. Right? After mid exam, 4 week, there will be a small Viva type. You will show me the progress of your model, how much I mean model and simulation you have done, and then in the last week, phase two mean last 2 week of the classes, then you have to submit the report of this project of this CEP, and then based on the report there will be the Viva and oral discussion. So is it clear?
yes, sir.
Okay.
Project individual है sir.
No, it's a group base. You can have maximum 3 people in a group. Okay. So there will be total, I think four maximum, yeah, maximum 4 groups there will be. That's a group project. You can have three people in a group, and it's not so difficult. I mean, if you are 3 people, that means one person can work on ORC, one person can work on the absorption, and the one can work on the solar. Solar is just a heat exchanger. I mean, water in, water out. Right? That's to produce the steam. That's just a 5 minutes job, maybe more than 5-10 minutes job. So then you basically, I mean, the ORC I have already presented in this class. The remaining is vapor absorption. So basically you have to develop vapor absorption cycle, and then you have to integrate the three system. So once you integrate the three system, then you have to analyze. Analyze mean you have to discuss this one, that how, what is the effect of the concentration of the lithium bromide solution on COP. I mean, if you change the concentration, how the COP is changing, and what is the effect of the generator temperature on COP, right? And then improve the vapor absorption system by preheating of the concentrated solution and pre-cooling of the lean solution, right? So that all will be in the form of graphs, in the form of table. I mean, the results will be presented, and then you can also discuss that what is the environment benefit of this system and what economics is involved. I know you have already done a lot of CEP, and you know that how to do such questions and how to perform the complex engineering problem. Yes, anything? I mean, on this one you can also perform directly the economic analysis. There is a extra tab that you need to install, that's called the economic analysis. So economic analysis can be performed on the same software. I mean, can you see this economics? There is a green button, economics. Can you see that? Is it
Yes, sir.
visible? Okay, so in economics you can perform the economic analysis. So it is off now, right now, but you can, I mean, it will ask you the component, it already know the components that are used here. It will ask you the what is the cost per year. So from you can put that cost. So it will automatically calculate all of the cost that are involved in the system. Right. Any other question? And from on Monday, there will be your quiz that will be related to the air refrigeration system at 6 p.m. Please don't forget the time, 6 p.m. No, we
Sir,
have class. Sorry, we have class at 4 p.m. So it will be at 4 p.m. Yes.
sir, we don't have a class on Monday.
No, but you have quiz. at
Okay.
4 p.m. The class will be on Wednesday and Friday.
And sir, is there an assignment session scheduled on Monday as well?
That's just a quiz session.
And what's the syllabus? Air refrigeration system.
Yeah, air refrigeration system
Okay, thank you,
that
sir.
we discussed previously. On Wednesday and Thursday, in on Wednesday and Friday, we'll try to complete the pre-mid syllabus. And one topic is remaining, and I hope you are already familiar with that. That's vapor compression refrigeration system. That's the conventional one. So we'll discuss. I hope we can wind up in the two lectures. Okay. Anything else?
सर सर टाइम 4 है या 6 है क्विज का?
टाइम जो है वो क्लास का टाइम है, आई मीन 4 p.m.
थैंक्स सर, थैंक
in
यू।
in LH1, the same classroom LH1.
सर मिड्स कब से स्टार्ट होगी?
Mid key, I have not received the date sheet, but one of you, one of the student was telling me that that's maybe from 16th November. So that means on 13 you will be free. So you have 2 days to prepare for the mid. Right? All right. See you then on Monday at 4 p.m. Okay. Allah Hafiz.